US Physics Olympiad year 2021. F equal MA, first round. As usual, it was given 75 minutes for 25 problems. If you want to get more interesting problems, just subscribe for this channel. The following information applies to problems 1 and 2. Problem number 1. At a time t equals 0, a small ball is released on the track shown with an initial rightward velocity. Assume the ball always rolls along the track without slipping. First problem. The ball starts at point A, turns around at point B, and returns to point A. Which of the following shows the speed of the ball as a function of time? Solution. The speed starts uniform, then uniform decreases to 0 as the ball reaches up the slope, and is instantaneously 0 when the ball is at point B. Then the ball speeds up again as it goes down the slope in negative direction, and returns to point A with the same speed it started with. So that's corresponding to graph A, and this is correct answer for problem number 1, and that was solution for problem number 1. Problem number 2. Which of the following shows the horizontal velocity of the ball as a function of time? Solution for problem number 2. The horizontal velocity is initially constant. As in the previous question, when the ball goes through the bend in the track, its speed is unchanged. However, the direction of its velocity quickly changes, so that only part of it is directed horizontally. Thus, the horizontal velocity very quickly drops. As the ball climbs up the hill till point B, its horizontal velocity decreases uniformly to 0, then very quickly increases in magnitude when it goes through the curve again. Therefore, the answer is E. And that was the solution for problem number 2. Problem number 3. Two massless rods are attached to frictionless pivots with their ends touching. The distances between the pivot points and the end points of the rods are shown below. Neglecting friction between the rods, if a force big F is applied at the left end of the left rod, what force F prime must be applied at the right end of the right rod to keep the system in equilibrium? Solution for problem number 3. Let's show the normal force between two rods. That's a small f acting on the right end of the left rod and on the left end of the right rod. To equalize equilibrium for the left rod, we must create force F small to apply this equation. For the left rod, we have equilibrium big F multiplied by r 2 meters equal small f multiplied by r 1 meter. For the right rod, we have F small multiplied by 0.5 meters equal F prime multiplied by R 2 meters. From here we have F small equal 2 big F and F prime equal 1/4 of small f, which is 1/2 of big F. And this is the answer B, and that was solution for problem number 3. Problem number 4. Alice and Bethany stand side by side on the Earth's equator. If Alice jumps directly upward in her frame of reference to a small height h, much less than the radius of the Earth, she will land a distance big D to the west of Bethany. If Alice had instead jumped to a height 2h, how far to the west of Bethany would she land? Neglect air resistance. Solution for problem number 4. Here we can find what is the total distance using formula distance d equal integral from 0 to 2 big T, where T is the time to jump from 0 to height h. V0 minus Vt, where V0 is initial tangential speed and the Vt is tangential speed on height h. So here we can use angular momentum conservation, because in case of a vertical jump we have angular momentum conservation. It means that V tangential multiplied by radius of Earth plus y, where y is current height, equals V0 multiplied by radius of Earth. Vy could be found from formula V initial vertical multiplied by time minus 1/2 gt square. And now Vt equal V0 r over r plus y. Here we can use that y over r is very small, so approximately we have Vt equal 1 minus y over big R. Initial Vi vertical we can find from formula Vi equal square root from 2gh, and the total time big T to jump from 0 to height h equal square root from 2h over g. Now we can put all this expression to our integral and find that distance big D equal this expression. Now after calculations we have that distance equal this expression, which is proportional to h power 3 over 2. It means that if we increase height twice, we have total distance equal 2 power 3 over 2d. This is answer E, and that was solution for problem number 4. Problem number 5. A train starts from city A and stops in city B. The distance between the cities is s. The train's maximal acceleration is a1 and its maximum deceleration is a2 in absolute value. What is the shortest time in which the train can travel between A and B? Solution for problem number 5. Obviously, we can reach the maximum average speed when we initially accelerate train till some kind of maximum speed, and after that constantly decelerate with the deceleration a2 to 0 speed, and in this time we reach the city B. So it means that now we can use equation maximum speed equal acceleration a multiplied by time t1 and equal deceleration a2 for time t2. From other hand, we have v average equal v maximum over 2. So it means that we can multiply total time t1 plus t2 by average, which is v maximum over 2, and that will be equal to total distance s. Now we can use first and third equations to count our times. From the first equation we can express v maximum through a1 and t1 and put it to the third equation, and also from first equation we can express t2. That will be a1 over a2 multiplied by t1, and insert it to the third equation. So we will get the equation a1 plus a2 multiplied by t1 square equal to a2 over a1 multiplied by s, and from here we can find what is time t1. That will be square root from 2s a2 over a1 multiplied by a1 plus a2, and using equation for t2 we can express it. That will be symmetrical to a1 and a2 compared to t1. Now we can count what is total time t. That will be t1 plus t2, and after all calculations we have this expression, which is answer C, and that was a solution for problem number 5. Problem number 6. A cylindrical bucket of a neglectable mass and radius r and height h, and is open at the top. It is submerged in water of density ρ, with its top distance h big below the surface. How much work is needed to pull the basket slowly so that its bottom is just above the lake surface? Solution for problem number 6. The problem can be solved using energy conservation. After the basket has been lifted, a mass m of water has been raised from the water surface to height small h over 2 above it, giving work mgh over 2, where mass m equal density of water ρ multiplied by volume pi r square h. So totally we have work equal ρ g pi r square h square over 2, which is answer D, and that was solution for problem number 6. Problem number 7. A point mass slides with the speed v on a frictionless horizontal surface between two fixed parallel walls, initially a distance big L apart. It bounces between the walls perfectly elastically. You move one of the walls toward the other by a distance 0.01 big L with a speed 0.0001 v. What is the final speed of the point mass? Solution for problem number 7. The total time to travel for this mass is approximately distance covered by the wall, which is 0.01 L, divided by speed of this wall, and we have 100 big L over v. For this time, ball travel distance v multiplied by time, which is 100 L. And because distance between collisions with the right wall is 2L, we can count that total number of collision with this wall is d over 2L, which is 50 times. After each collision, the speed of the ball increases by 0.0002 v, because that's elastic collision with the wall. And the total change of speed is delta big V equal delta small v multiplied by number of collisions, which is 0.01 v. It means that the total final speed of this ball is v plus delta big V, which is 1.01 v. That's answer D, and that was a solution for problem number 7. Problem number 8. A mint produces 100,000 coins. Upon weighting some of them with a precise scale, officials find that the coins vary slightly in weight with an independent uncertainty of 1%. About how many coins must be randomly sampled and weighted in order to determine the total weight of the coins with a 0.1% uncertainty. Assume there are no sources of systematic uncertainty. Solution for problem number 8. If we have independent uncertainties, we can use formula that uncertainty for total mass delta n equal square root from number of coins multiplied by uncertainty for one coin. Total mass equal number of coins multiplied by mass of coin. So we can just divide first formula by second formula, and we have this relation. In this formula we need uncertainty for total mass equal 0.1% or 0.001. Uncertainty for one coin is 0.01. So it means that combining all these expressions, we can find that number of coins equal 100. And this is answer D, and that was solution for problem number 8. Problem number 9. NASA trains astronauts to experience weightlessness with an airplane which flies at a parabolic arc with a constant acceleration g downward the ground. The plane can remain on this trajectory for at most 25 seconds due to the large change in altitude required. If instead of simulating weightlessness, NASA wanted to fly a trajectory that would simulate the gravitational acceleration of Mars, 3.7 meters per second square. For what length of the time can the plane simulate Mars gravity? Assume that the maximum change in altitude is the same for both trajectories. Solution for problem number 9. First, we can find what is the change of altitude. For that, we can use formula h equal 1/2 gt square. Here, total time is 25 seconds, but this is for trajectory up and down. So it means that for time we have to use half of this 25 seconds. So it means that total change of height is 766 meters. After that we can find which acceleration need to use airplane to simulate acceleration of gravity on Mars. That will be a equal g minus a0, where a0 it's gravitational acceleration on Mars. So that will be 6.1 meters per second square. And now we can count what is total time for motion up. That will be this expression. So it means that to move it up we need 15.8 seconds. And we have to double this time for motion up and down, which give us approximately 31.6 seconds. This answer is closest to answer B, 31 seconds. And that was a solution for problem number 9. Problem number 10. A uniform solid circular disk of mass m is on a flat, frictionless horizontal table. The center of mass of the disk is at rest and the disk is spinning with angular frequency omega 0. A stone modeled as a point object also of mass m is placed on the edge of the disk with zero initial velocity relative to the table. A rim built into the disk constrains the stone to slide with a friction along the disk's edge. After the stone stops sliding with respect to the disk, what is the angular frequency of rotation of the disk and the stone together. Solution for problem number 10. Here we can use angular momentum conservation. So we have angular momentum equal I0 multiplied by omega 0, where I0 for solid disk is 1/2 m r square. Now when we put this stone on the edge of this disk, we still have the same angular momentum, but now all construction rotates around common center of mass, which stay on a distance r/2 from the center of the disk. So it means that for this construction we need to count what is moment of inertia. For stone that will be m multiplied by r/2 square, and for disk that will be this expression. Here we use a parallel access theorem. So it means that the total moment of inertia for this system around the center of mass equal mr square. Now we can use angular momentum conservation. I multiplied by nu omega equal I0 multiplied by omega 0, and the final frequency will be omega 0/2, which is answer C, and that was solution for problem number 10. Problem number 11. Projectiles A, B, and C are simultaneously thrown off a cliff and take the trajectories shown. Neglecting air resistance, rank the times TE, TB, and the TC they take to hit the ground. Solution for problem number 11. Since the x and the y directions are independent, the time to impact only depends on the initial vertical speed, which in turn determines the maximum height. The higher the maximum height, the longer the trajectory takes. In our case, highest trajectory is B, next one is A, and the lowest is C. So it means that the correct answer is D. That was a solution for problem number 11. Problem number 12. An object of mass small m equal 1 kg is attached to a platform of mass big M 4 kg with a spring of spring constant K equal 400 newtons per meter. There is no friction between the object and the platform, and the coefficient of static friction between the platform and the ground is mu equal 0.1. The object is placed at its equilibrium position and then given an horizontal velocity v. For what v will the platform never slip on the ground? Solution for problem number 12. First, let's count what is the force acting on the platform. That will be kx, where x is displacement. This displacement could be found from energy conservation. So we have 1/2 kx square equal 1/2 mv square. From here we can find what is x. That will be v multiplied by square root from m over k, and the force acting from the spring on the platform equal v multiplied by square root from mk. This force cannot exceed the force of friction. Maximum force of friction equal mu multiplied by small m plus big M multiplied by g, and we have to equalize this force of friction to force from spring to platform. That will be this equation, and from here we can find what is speed v. That will be this expression, and after putting numbers we have 0.25 meters per second. This is the critical speed, which corresponding to answer C. Basically, answer A and answer B are correct too, but answer C is most allowable. So it means that the correct answer is C, and that was solution for problem number 12. Problem number 13. A car is driving on a semicircular racetrack. Its velocity at several points along the track is shown below. Which of the following could depict its acceleration at the corresponding points? Solution for problem number 13. Because the car is speeding up, its acceleration has a tangential component. It means that a component parallel to the racetrack. Because the car is turning, its acceleration also has a component v square over r directed towards the center of the track. Since v increases throughout the turn, this inward radial acceleration increases through the turn. For picture A, we have only tangential acceleration, which is not good. For picture B, we have only centripetal acceleration, and also constant, which is not good. For picture C, we have only centripetal acceleration, which is increasing, but we don't have tangential acceleration. And for picture E, we have acceleration constant in value, and we see that our acceleration must increase, so it's not good. And only picture D could correspond correct answer, because the value of acceleration is increasing, it has a tangential acceleration, and centripetal acceleration is increasing. So that's only correct answer is D, and that was solution for problem number 13. Problem number 14. A bacterium cell swims by rotating its bundle of flagella to counter a viscous drag force in the medium. The drag force F as a function of r, v, and nu only depends on the typical length scale of the cell r, its speed v, and the viscosity of the fluid nu, which has units of kilogram over meters by seconds. It is observed under a microscope that a cell of length 1 micron swims at about 20 microns per second. Estimate the speed of a cell of length 0.5 microns, assuming cells of all sizes generate the same amount of force from their flagella. Solution for problem number 14. Using dimensional analysis, we can see that force scale F could be found from this equation. Here on the right we have a combination of different powers for R, V, and nu. The only solution for this equation is A equal B equal C equal 1. So it means that force F proportional to R, V, nu. It means that if we decrease size twice, we have to increase speed twice. So it means that correct answer is C, and that was solution for problem number 14. Problem number 15. A block is released from rest at the top of a fixed frictionless ramp with horizontal length L and the inclination theta. For a fixed value of L, which value of theta minimizes the time needed for the block to reach the bottom of the ramp? Solution for problem number 15. Here we can use kinematic equation which connect length, acceleration, and time. Total length of this incline is L over cosine theta. Acceleration is g sine theta. And from this formula we can find that t square equal L over g, multiplied by 1 over sine 2 theta. And we have to find the minimum for this function. Minimum for this function will be for sine 2 theta equal 1, because it's maximum. It means that 2 theta equal 90 degrees and theta equal 45 degrees. This is answer B, and that was solution for problem number 15. Problem number 16. The particle begins at the point x equals 0 and moves along the x-axis with initial rightward velocity v0. Later the particle reaches the point x equals L. The velocity as a function of position during this time interval is shown below. Consider the following three statements. First, the particle instantaneously stops at x equals L. Second, the particle is uniformly accelerated. Third, the particle could be performing simple harmonic motion. Which of these statements are true? Solution for problem number 16. Let's check all three statements. First, the particle instantaneously stops at x equals L. This is correct because when particle reaches point L, it will stop and it will not move further. So first is correct. Second, the particle is uniformly accelerated. For uniformly accelerated particle, x behaves as a parabola and v behaves as straight line. So it means that v as a function of x cannot be straight line. Third, the particle could be performing simple harmonic motion. This is not correct because simple harmonic motion, if displacement behaves like sine omega t, velocity behaves like cosine omega t, and dependency of velocity from displacement is not straight line. So it means that correct answer is A, only first one. And that was a solution for problem number 16. Problem number 17. In a certain country, the short hand of a clock is exactly half as long as the long hand and rotates twice for each rotation of the long hand. The 3 points shown on the clock hands have acceleration of magnitude AA, AB and AC. The point B is at the midpoint of the long hand. Which of the following is true? Solution for problem number 17. Let's a length of short hand is small r, and the angular velocity of big hand is omega. Total centripetal acceleration equal omega square r. So it means that for point A we have acceleration equal omega square multiplied by 2r, which is 2 omega square r. For point B we have acceleration equal omega square r, and for point C we have acceleration equal 2 omega square multiplied by r, which is 4 omega square r. And from here we see that AC is greatest, next one is AA, and lowest is AB. This is answer C, and that was a solution for problem number 17. Problem number 18. A factory's smokestack continuously produces smoke. The smoke always rises with a constant speed relative to the air around it. Suppose that the air was initially still, then abruptly started blowing to the right, then abruptly became still again for some time. Which of the following could show the resulting shape of the smoke plume? Solution for problem number 18. The smoke right next to the smokestack has just been emitted and has only been exposed to still air, so it must rise straight upward. This rules out choice A. The smoke high above the smokestack has experienced the full duration of the rightward wind, so it all must have been pulled to the right by the same amount, ruling out choices C and D. Finally, the smoke in between has been exposed to only part of the rightward gust of wind, since some of that wind occurs before that smoke left the smokestack, so its path should smoothly connect the vertical segments. This rules out choice E, leaving B as a correct answer. So that was a solution for problem number 18. Problem number 19. A cavity of radius r over 2 is dug out of a spherical planet with a uniform mass density of mass m and radius r. What is the magnitude of the gravitational field at point P in the diagram below? Solution for problem number 19. Solution for this problem could be created using vector form. Let's draw this picture with a gravitational field for full sphere is E1. Gravitational field for part of this sphere is E2, and E is gravitational field for our figure with the cavity. So it means that E1 equal E plus E2, and from here we can find that gravitational field for our figure with the cavity equal vector E1 minus vector E2, or using cosine form for vectors we have this form where theta, that's the angle between vector E1 and E2. Now we can write that E1 equal G multiplied by mass over R square, E2 equal G multiplied by mass of small sphere, which is m over 8, divided by 5 over 4 r square, where distance from center of this small sphere to point P equal square root from 5 over 2 r. And we have E2 equal 1 over 10 g m over r square. And for angle theta we have cosine theta equal 2 over square root from 5. Now we have E square equal this expression, which is 0.831 E1 square, or finally we have gravitational field equal 0.912 gm over r square. That's answer E, and that was solution for problem number 19. Problem number 20. The line between day and night on a planet or moon is called the terminator. How fast does the terminator of Earth's moon move across its surface at the equator? The radius of the moon is 1.74 multiplied by 10 power 6 meters. Solution for problem number 20. The same side of the moon always faces Earth. This means the terminator runs all the way around the moon once per month. So the speed equal
2 pi multiplied by radius of moon and divided by 28 days, which is approximately 4.5 meters per second. This is answer B, and that was solution for problem number 20. Problem number 21. A solid sphere sits at the top of a ramp of a height h inclined at angle theta to the horizontal. Both the static and the kinetic coefficients of friction between the sphere and the incline are mu k equal mu s equal 0.2. The sphere is released from rest at the top of the incline. For which of the following values of theta is the total translational plus rotational kinetic energy of the sphere greatest when it reached the bottom of the incline? Solution for problem number 21. The maximum translational and rotational kinetic energy possible when the motion of sphere is without sliding. In that case, force of friction doing zero work and the whole rotational potential energy turning to kinetic energy for translational rotation. It means that we have to find the critical angle for which this is possible. Let's write two equations for translation and rotation. For translation we have ma equal mg sine theta minus force of friction F. For rotation we have I alpha equal Fr. For solid sphere, moment of inertia I equal 2 over 5 mr square. And the condition for sliding give us angular acceleration alpha equal acceleration a over radius of the sphere r. Let's put this to the second equation. We will get that force of friction will be equal to 2 over 5 ma. We can put this to the first equation and define what is acceleration. That will be 5 over 7 g sine theta. And now we can calculate what is force of friction. Force of friction will be 2 over 7 mg sine theta, which cannot exceed maximum possible force of friction, which is mu multiplied by normal force, which is mg cosine theta. And from this inequation we can find that tangent theta must be less or equal to 7 over 2 mu, which will give us a critical angle 35 degrees. For angles less than 35 degrees, we don't have any energy loss. It means that the correct answer is A, 10 degrees. And this was a solution for problem number 21. Problem number 22. A ship rams into a hunk of ice floating in the sea. Icebreakers are ships designed so that when this happens, the ice is pushed down beneath the ship. If the coefficient of static and kinematic friction between the ice and the ship is mu, what condition applies to the angle theta as shown in the figure, so that the icebreaker functions as intended? Solution for problem number 22. There is a force from the ship on the ice, which may be broken into a normal force and a friction force. The vertical component of the normal force is negative n multiplied by cosine theta, and the vertical component of the friction force is F multiplied by sine theta. The friction force can be at most mu n, so the vertical force from the ship on the ice is Fy less or equal than mu n sine theta minus n cosine theta. And from here, because force Fy must be less than 0. We have cotangent theta must be greater than mu, which is answer A, and that was a solution for problem number 22. Problem number 23. An imperfect spring has a restoring force F that depends on the displacement x from equilibrium as in the graph shown below. The slope of the curve for x less than negative d and x greater than d is a constant k. A mass m is attached to the spring and released from rest at the position x equal a, where a greater than d. What is the period of the subsequent motion? Solution for problem number 23. On this graph we can see that motion from point D to point A is perfectly harmonic motion, same as from negative D to negative A. It means that we can count what is the period of this motion, except motion with a constant speed between negative D and D. That will be T1 equal 2 pi multiplied by square root from m over k. Now let's count what is the speed of this mass during motion from negative d to d and back. That we can count from energy conservation. And from here v equal square root from k over m multiplied by a minus d. And now we can count what is time to move object from negative d to d and back from d to negative d. That will be 4d over v, or this expression. And finally total time equal t1 plus t2, or this expression, which is answer C, and that was a solution for problem number 23. Problem number 24. Two satellites are in circular orbits around a star with equal radius r, speed v and the period t. The satellites are initially diametrically opposite each other. In order to meet a second satellite in time t over 2, the first satellite should decrease its speed to approximately next one. Solution for problem number 24. First, let's use third Kepler law to count what is the size of a semi-major axis for second satellite. We have this relation, that cubes of a semi-major axis equal to squares of periods, which in our case 1 over 4. It means that for the second satellite, semi-major axis equal this expression. Now let's use equations for total energy. For the first satellite we have total energy equal negative g m over 2r. And for second satellite, total energy equal negative g m over 2a. Now let's count what is energy difference. E1 minus E2 equal this expression, or because in initial points potential energies are equal, it will be difference in kinetic energies. Also we can use expression for circular orbit, that v square equal g multiplied by m over r. Now we can put this expression to this expression and find a relation between v and v2. From here we can find that v2 square equal approximately 0.41 v square, or v2 equal approximately 0.64 v, which is answer B, and that was solution for problem number 24. Problem number 25. Displacement Fred's trusty pellet sprayer is held at rest a distance h away from the center of a planet orb, which has radius big R much less than H. The pellet sprayer ejects the pellets radially outward, uniformly in the plane of the page. These pellets are all launched with the same speed v, so that a pellet launched directly away from orbit by the pellet sprayer can just barely escape it. What fraction of the pellets eventually lands on orb? Hint: you may use the small angle approximation sin theta approximately equal theta for theta much less than 1, where theta is in radians. On left picture we have the pellet sprayer relative to orb, and on the right picture we have a close-up of the pellet sprayer. Solution for problem number 25. Because all pellets are launched at the escape velocity, the speed of one of these pellets, a distance small r away from orb, is square root from 2gm over small r. At a distance r minimum of closest approach, the pellet's velocity must be perpendicular to its displacement from the planet's center. Then, by conservation of angular momentum for a pellet of mass m launched at angle theta from the vertical, we have mv h sin theta maximum equal mv in point big R multiplied by big R. The pellet collides with the planet whenever r minimum less than big R. Then our equation for theta maximum is this one for small theta. From here we can find that theta maximum equal square root from big R over h, and the range of collisions angle is thus between negative theta maximum and positive theta maximum, and the range of all of it angles is 2 pi, so the fraction is 2 theta maximum over 2 pi, which is 1 over pi multiplied by square root from big R over h. This is the answer E, and that was solution for problem number 25.